Welcome to Math with Professor V. In this video, we're going to go over how to graph rational functions. Now, this video is intended for pre-calculus, college algebra students, not calculus students unless you're doing a little review. If you are in calculus and you need help graphing rational functions because you have to find critical points, local extrema, etc., then I have a different video for you and I'll link it right here. Click in the top right. I'll put it in the description also. This video won't hurt you, but I'm not going to use any calculus while graphing because this is intended for pre-calc. Okay? Anyways, let's hop to it then. So, what is a rational function? It's when you have a function that is a ratio of two polynomials. So we can represent f of x as some polynomial, we'll call it p of x over q of x. Okay? Polynomial in the top, polynomial in the bottom. A fraction, basically. So here's the steps that I like to follow. If you would like to take a screenshot, now's your chance. There you go. Did you get your screenshot? Okay, now let's go over the steps so you understand, and then I have some examples for you. So the first thing you need to do is factor completely and find the domain. So you're going to factor p of x, you're going to factor q of x, and find the domain. Remember, when we're talking about a rational function, our domain is restricted anytime q of x is equal to 0. So whenever the denominator is 0, those x values have to be removed from the domain. And then after you've written the domain, you reduce to lowest terms if necessary, meaning if you can cancel out any common factors for p of x and q of x, you do that. But make sure you list the domain first before you do any canceling, okay? After that, you're going to find the x and y intercepts. X-intercepts come from when the function's equal to 0. You would just set p of x equal to 0, and then y-intercept comes from plugging in or substituting in 0 for x. That should be pretty straightforward. Step 3, you're going to find all asymptotes. So here's the types to look out for. First, vertical. Once f of x is reduced to lowest terms, meaning you've already canceled any common factors if there are any, then the zeros of the denominator give the equations of the vertical asymptotes. So you could have x equals whatever the zeros of the denominator are, and you could have multiple vertical asymptotes. They're always in the form x equals some number because they have to be vertical lines, okay? Horizontal asymptote. Now remember, we have p of x in the numerator and q of x in the denominator. In fact, let me just bring that down so you can still see it while we're looking at this situation here, okay? So if the degree of p of x, the numerator, is less than the degree of q of x, the denominator, then your horizontal asymptote is at y equals 0. So if the highest power of x in the top is smaller than the highest power of x in the bottom, automatically horizontal asymptote is y equals 0. If you're a calculus student, this should make sense because when you take the limit to infinity, it would be 0. Now, if the degree of the numerator is equal to the degree of the denominator, then what you do is you take the ratio of the leading terms, you take the ratio of the coefficients of the leading terms, and that gives you the equation of the horizontal asymptote. So say p of x has the form a x to the n plus blah, 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 and then q of x is b x to the n plus blah, 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 blah. Then here's your horizontal asymptote. It's just going to be a divided by b. So you take the coefficients of the leading terms and you put p of x is in the top, q of x is in the bottom. Boom. Okay, now last case, if the degree of the numerator is greater than the degree of the denominator, then you don't have a horizontal asymptote. If the degree of the numerator is exactly 1 greater than the degree of the denominator, then you have a slant or oblique asymptote and you long divide to find it. And you might be wondering, well, what if it's more than 1 greater? If it's 2 greater, you can have a parabolic asymptote. I don't make my students do those problems. I really would be shocked. Tell me if you have to graph any rational functions with parabolic asymptotes and I'll do an example for you. But I have yet to find someone who assigns those. Okay. So basically 1 degree higher, it's a slant oblique asymptote, and we long divide. Don't synthetic divide. You're not allowed. It won't give you the right answer always. So just don't do it. And then last, put together your graph. You might need to test intervals or find more points depending on where everything kind of falls together. So I'll show you what I mean when we get into some examples, okay? You have to have a nice attitude about graphing, because students always complain like, I hate graphing. It's just, it can be a little scary, right? When you're putting all the steps together, and it can be tedious. But if you just kind of enjoy it and go with the flow, just go, I'm in the moment, you know, I'm doing my thing, it won't be so bad. So here we go. Graph the following rational functions using the steps outlined above. And the first step says factor completely and find the domain, okay? So let's factor both the numerator and denominator. The numerator is x squared minus 6x plus 8. So that factors into x minus 4 times x minus 2. And the denominator factors into x minus 6, x plus 6. Good? Okay, so first things first, the domain. I have to restrict x equaling 6 and negative 6 from the domain, because both of those values would make the denominator equal 0, which then would make the rational function undefined. So the way I say that is my domain, and then you write a set. It's the set of all x's such that x cannot be positive or negative 6. And when you write your domain this way, it's assumed all other values of x are fine. Any real value except negative 6 and positive 6 is good to go. This is set builder notation. If you were to write it in interval notation, it's just not as succinct, but we could. How do you say all real numbers except plus or minus 6? You would go negative infinity to negative 6, union negative 6 to 6, union 6 to infinity, with parentheses on all of these negative 6s and positive 6s, because we're skipping over them basically, okay? So I let my students pick whichever form they want to write the domain in depending on the function, but should your professor or instructor specify, this is set builder, this is interval, okay? Good. And then the rest of step 1 says reduce to lowest terms if necessary, but it's not necessary. Notice none of these factors are the same in the numerator and denominator, so nothing's going to cancel out, okay? So then now let's go ahead. Let's find the x and y intercepts. So let me show you a cool shortcut. Maybe you already noticed it, so great. X-intercepts come from setting y, or f of x, equal to 0, right? If I set f of x equal to 0, and I'm going to use the factored form because why not? Half the work's already done. If you set f of x equal to 0, anytime you have a rational function, the first step in solving this equation is you would multiply both sides by the denominator, correct? And then notice what happens. Well, since I have a 0 on the other side, I'm just going to get 0 equals the numerator of the rational function. So I didn't even need to do this step, and I won't ever do it again in the rest of the video. That's how much I've just had it with that step. So when you need to find the x-intercepts for a rational function, literally just look at where the numerator is 0, as long as it's in lowest terms, okay? And then boom, look, it's factored. I can tell really clearly x-intercepts are at 4 and 2. However, I'm going to advise you don't write your answer like that. Otherwise, you might get mixed up and think those are equations of vertical asymptotes. Who knows, right? X-intercepts are points. They're points on the graph. So I'm going to write them as ordered pairs. That way it's super duper clear. These are not equations of vertical lines, okay? So here's my lovely x-intercepts. Come on. Beautiful. Okay. Oh, Lordy. Okay, now y-intercepts. Y-intercepts come from substituting in 0 for x. So I'm going to plug in 0 for x. Honestly, the easier place to plug it in is before we factored, because there's more work to do if you plug it into the factored version. So I'm going to plug it into this one, okay? So y-intercept is f of 0, which is going to be 8 over negative 36. That reduces, right? I could divide by 4 and never leave a negative in the denominator. Put it outside or in the numerator. So this is negative 2 over 9. So my y-intercept is at 0, negative 2 over 9. How are we doing? Okay, good. Now, we're going to move on and find all of our asymptotes. So, step 3, let me do it right here. Vertical asymptotes. Everything's already in lowest terms because nothing canceled out. So the equations of my vertical asymptotes come from where the denominator is 0. It's precisely the domain restriction, actually. So the vertical asymptotes are at x equals 6 and x equals negative 6. Do you see now why I didn't want you writing this as x equals 4 and 2 and leaving it that way? Because then it would be misleading. Which one are your asymptotes? Which one are your x-intercepts? So write your intercepts as ordered pairs. Now let's look to figure out, do we have a horizontal asymptote? Do we have an oblique asymptote? Neither. What's going on? So you first need to identify the degree of the numerator and the degree of the denominator. So you look at the highest power of x. The numerator is degree 2. And then you look at the highest power of x down here. It's also degree 2. So when they're equal, you look at the coefficients of the leading terms. So the coefficients are just a 1 for each of these, right? It's 1x squared, 1x squared. So then your horizontal asymptote would have the equation y equals 1 divided by 1, which is just 1. So y equals 1 is the equation of our horizontal asymptote. You just take 1 divided by 1, like that. Okay, so let's put it all together. Since I have 2 vertical asymptotes, my graph is going to be broken up into 3 pieces. However many vertical asymptotes you have, that breaks it up into 1 more piece than that. Okay, so 2 vertical asymptotes, 3 pieces. 4 vertical asymptotes, 5 pieces. 1 vertical asymptote, 2 pieces. N vertical asymptotes, n plus 1 pieces. Yes. Okay, let's put the graph together. Do you have all this info? Because I do. So I'm going to draw the graph down here. I just want to make sure you can reference all the lovely info we found. Okay. So we got to go all the way out to 6 and negative 6. And I'm not going to, whoa, what happened? I'm not going to scale my axes the same because do you see how the y-intercept is negative 2/9? And the horizontal asymptote's just at 1. So I'm going to really like spread this guy out. This is 1, 2, 3, you know, negative 1, negative 2, negative 3. But then in the x-axis, I'm going to squish it a little more. This is 2, 4, 6, 8, 10. Oh, yeah. I will give my students, you know, a little grid, but I don't scale it. I let them do what they want because, you know, depending on the problem, you may want it differently. Okay, let's put our asymptotes in and our intercepts in, all right? So notice here we had x-intercepts 4, 0, 2, 0, 4, 0, 2, 0. And then I have a y-intercept 0, negative 2/9. So it's like negative 0.2 repeating. Let's see, right here. Okay, and then let's put in our asymptotes. So we've got x equals 6, x equals negative 6. Those are vertical, and y equals 1. So draw a dashed line for each of those. So here's x equals 6. X equals negative 6. And then y equals 1. Okay, now I told you there's 3 pieces to the graph, right? And you do need to remember what y equals 1 over x looks like. Y equals 1 over x is kind of like your foundation, your parent function for rational functions. And 1 over x has 1 piece here and 1 piece here. So the outermost pieces of our graph, because we have 1, 2, 3 pieces, because here's a vertical asymptote, here's a vertical asymptote. On the outsides, it's going to resemble 1 over x, and then in the middle, we got to figure out what's going on, but I can kind of already tell based on the points that we have, okay? So here we go. Let's go piece by piece. On this piece right here, to the right of this vertical asymptote, okay, you have 2 options. Either your graph is going to look like this or it's going to look like this. but you should already be able to eliminate one of those. This guy is not an option because if it was, we would have had another x-intercept, and we only found 2 and 4 as our x-intercepts. So don't draw something which crosses the x-axis again. That makes no sense. So this is not possible. It has to look like this. And then if you're in calculus, you do things like find concavity, etc., and you know that the function is decreasing on that interval, so then you would already know how it should look. But even without calculus, we know it's got to be up here. And if you want to plug a point in, you can, but this is more than enough, okay? Good, let's do the other outside piece. Is it going to be here or here? Let me show you your options. Is it going to be here or is it going to be here? And those are the only options. It's got to look like 1 over x. Well, again, we can't cross the x-axis here because we found the 2 x-intercepts. Neither of them was negative over there, so it's got to be up here. Something like this. Okay? Good. Now, in the middle, notice we don't have a lot of options. It'll look either like x cubed, negative x cubed, some sort of parabola this way, or some sort of deform-ish parabola. You know, not really a parabola. I can already tell, since I can't cross the x-axis again, right? I know this isn't happening. That makes no sense. So it's coming through, and then it just has to go back down. It can't do anything else. If I do anything else, then I'm crossing the x-axis extra, and we're not allowed to. So it's going to look like that. It looks kind of like a downward parabola, but a deformed one. It's fine. It's fine. It's deformed. We love it anyways. So here we go. There. Now, exactly how high do you go? When you're in calculus, you would find the local max and you would know. When you're in pre-calc or college algebra or whatever, you just get to do whatever you want and you just turn it around at some point and no one's upset with you. They're just happy you made it this far, okay? So note, if you are in calculus, you would have to find that critical value, that local max, but we're just doing it for pre-calc level, okay? There you go, that's it, we're done. That wasn't too bad. That was actually fun. Let's try another, yeah? Okay. F of x equals x over x squared minus 4. So step 1, factor, find the domain. So the numerator, nothing to factor. Denominator factors into x minus 2 times x plus 2. So I have 2 restrictions in the domain, right? All x's such that x can't equal plus or minus 2. And then there's nothing to reduce. It's already in lowest terms. Okay. Now let's get the x-intercept. Remember, you can just take the shortcut, set the numerator to 0. So you would get x is 0, which means 0, 0 is my x-intercept. It's also my y-intercept. So that's it, just one intercept. Okay, now it's time for asymptotes. Do we have vertical asymptotes? Oh yeah. Look at the denominator, x equals 2 and x equals negative 2 are my vertical asymptotes. Now, do we have a horizontal asymptote? What's going on? So the degree of the numerator, it's degree 1 because we have x to the first. And then the denominator is degree 2. When the denominator is a higher degree than the numerator, automatically your horizontal asymptote is at y equals 0. You don't have to do anything. And this could have been x cubed, x to the 4th, x to the 100. If it's a higher power than the numerator, automatically y equals 0. Okay? So that's it. Now let's put on the graph everything that we have. And since, you know, we found less points than last time, we might need to test some intervals. So I'll show you how to do that, okay? X and y. We have to go to 2 and negative 2. Okay. And then here's my vertical asymptotes. Boop, 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 boom. And then horizontal asymptote is y equals 0. So just kind of remind yourself, since it's the x-axis, put a little dashed stuff at the end so you don't forget, okay? So how many pieces are we going to have in this graph? There's going to be 3, right? Okay, so let's start over here. Is it going to be up here or is it going to be down here? Honestly, we don't know. We have to check. So unlike last time, we have a little more work to do. So how do you check? You go, okay, well over here, all of the x values are bigger than 2. So pick any number that you like and you're going to plug it in for x and see what the y value is. And it honestly, you don't have to be too precise about plotting the point. I just want to know, is it positive or is it negative, the y value, okay? So say 3. I'm going to take f of 3. F of 3 is 3 over 3 squared minus 4. That's 3 over 9 minus 4, so that's going to be positive. So then I know, oh, the graph lives up here, okay? Not down below. So let me put it right here. And notice, like, I didn't care what number this was to make sure I came here and, like, found it. We're good. Okay, now the next piece. We have this intercept at 0, 0. So I know the graph goes through this point, but I don't know much else. Like, it could look like this. It could look like this. It could look like this, or like this. Those are the main 4 choices for the middle, right? So we're going to have to check on both sides, right? Because I don't know, does it stay on the same side or does it switch sides? So that's why we're going to have to plug in maybe 1 and -1, okay? So f of 1 is going to be 1 over 1 squared minus 4. So that's negative, because 1 squared minus 4 is negative. So it's down here somewhere. And then f of -1 would be -1 over -1 squared minus 4. That's positive, because this would be -3 and then -1. So overall it's positive. So it's looking kind of like x cubed flipped in the middle. Good? Okay, and then the last piece, actually I already know where it's going to go because this is an odd function, but I didn't tell you to test for symmetry. That's just like a bonus. I don't know if you remember testing for symmetry, whether or not a function is even, odd, or neither. I'll link a video if you need to review that concept. It's, you know, students are always like, this is so annoying. But then when you're graphing, it saves you time because I can tell by looking it's odd. So I know the last piece is going to be down here. But if you forgot that, it's no big deal. You're fine. You're totally fine. We're going to test somebody over here so I know whether or not the graph is here or here. Let's pick -3 for x. So f of -3 would be -3 over -3 squared minus 4. So this would be positive. This is negative. So overall, it's negative. So it's going to be this piece down here. Okay. Good? So see how this one, even after finding all the intercepts and everything, we still needed more info to put the graph together. That happens sometimes. Okay? And then if you're in calculus, well, you would be finding the concavity, and figuring out where it's increasing, where it's decreasing. So that should be enough. You would know the graph's concave up here. You can't draw it down here and make it concave up. The graph is concave down here. You couldn't draw it somewhere else. You couldn't draw it here and make it concave down like that. Okay, so don't be scared, you guys. When you go to calculus, it just makes graphing easier. There's more steps to do, but it gives you more information. So don't be scared. It's beautiful. It's so beautiful. All right, I got 2 more for you. This is a fun one. Okay, f of x equals x squared plus x minus 2 over x squared minus x minus 6. So step 1, let's factor everything. The numerator factors into x plus 2 times x minus 1. And then the denominator factors into x minus 3 times x plus 2. Now, I know you're probably tempted to cancel x plus 2, but not yet. Remember, step 1, write the domain using the original function. So we have 2 values of x that need to be restricted from the domain. X can't be 3 or -2, yeah? Okay, now, oh my God, I'm writing so crooked, sorry. Let me get it together. Okay, now we can go ahead, let's cancel out x plus 2. And for the remainder of the problem, you don't need to look at the original anymore. We're gonna work with the reduced form version, y equals x minus 1 over x minus 3. And you might say, but what the heck is going on at x equals negative 2 then? We actually have a hole in our graph. Yes. What's a hole? It's literally just like an open circle in the graph. It's like someone came along to the graph and plucked out one of the points. How dare they? There's a hole in our graph at x equals negative 2. And you want to know what's the y value where the hole is at, so you can plot a cute little open circle on your graph. So where do you go to figure out the y value? Not here. You go to the reduced form version and you plug in negative 2 for x. So let's do that really quick. So y of negative 2 would be negative 2 minus 1 over negative 2 minus 3. So that's negative 3 over negative 5, which is positive 3/5. So we have a hole in the graph at negative 2, comma 3/5. You're just going to graph an open circle. So what happens is negative 2 is not in the domain, but because it canceled out, it was a factor that was also repeated in the numerator. It's called a removable discontinuity. It is a hole in the graph. We only have one vertical asymptote because you look at the reduced version of the original function when finding your asymptotes. This discontinuity at x equals 3 is not removable, and that's what you're going to learn in calculus. That's where you have a vertical asymptote. But just think of it this way. When it cancels out, it's not as dangerous, right? We can remove it and fix this discontinuity by simply redefining our function. And it's beautiful. You'll learn more about that next semester. And pre-calculus, it's so lovely. You do all this math and you're just kind of taught the rules, right? I just told you if it cancels, it's a hole. But the why behind it, you'll see that when you get to calculus, and all your questions will be answered. It'll be just a lovely moment for you. Okay, anyways, I'm getting too excited. Let's go find our intercepts. So now we need x-intercept, y-intercept. X-intercept, use the shortcut, just set the numerator to 0. And just set the reduced guy's numerator to 0. Yes, forget him. That was a mess, right? We have this nice simpler version. So I'm just going to set x minus 1 equal to 0, which gives me x equals 1. But an intercept, write it as an ordered pair, so you remember it's a point, 1, 0. Y-intercept, I'm going to plug in 0 for x. Plug it in, yes, to this reduced one. If you did it here, you'd get the same thing, but use the easy one. Make life nice on yourself. Y, it's hard enough already, right? So why don't do things the harder way? Negative 1 over negative 3 is positive 1/3. So y-intercept is 0, 1/3. Okay, I love it. I love it so much. Asymptotes. We kind of already talked about it, yeah? So vertical asymptotes, we only have one because you look at the reduced form and it's going to be at x equals 3. Do we have horizontal? What's going on? It doesn't matter which version you use. You could look at the original. You could look at the reduced. Let's look at the reduced. Numerator is degree 1 because this is x to the first. Denominator also degree 1. When they have the same degree, you look at the leading coefficients, which are just both 1s, and you take their ratio, 1 divided by 1. So horizontal asymptote is at y equals 1. Okay, we have a lot to put on our graph. Hopefully it's enough. One vertical asymptote, so our graph is going to be in 2 pieces. We've got a hole and 2 intercepts. I'm excited. Also, if you're not the biggest fan of graphing, here's how you can be. You just brainwash yourself. You lie to yourself as you're graphing. You go, this is so fun. I love it. Like right now, I noticed I just said I'm so excited, but I really am. If you keep telling yourself something, you can brainwash yourself. Yes, try it. 1, 2, 3. There's my vertical asymptote. 4, 5. I'll just match it on the other side. 1, 2, 3, 4, 5. And then We have to go to, these are so small, 1/3, 3/5. Let me really, 1, 2. Oh yeah, horizontal asymptote was at 1. Okay, that looks beautiful. So let's put our asymptotes in. Horizontal asymptote, y equals 1, coming in hot. X equals 3, vertical asymptote. Have you graphed anything with the hole before? It's quite fun. Yes. So we've got -2 3/5. And I'm going to put an open circle. See, that's the hole. -2 3/5. 1, 0 is an x-intercept. Okay. 1, 0. There you go. 0, 1/3 is my y-intercept. And I think we are in business, yes? Because this piece of the graph has to go this way. No other choice. Do we want this just a smidge thicker? I say yes. Here you go. Here you go. Woo! Now, what about the other side? Is it going to be here or here? You should know conclusively. This is a no-go because then we'd have another x-intercept, right? So I don't even need to test. I know it's up here. Minding its business. Are you putting arrows on the endpoints? Make sure you are. Minus a half a point if you don't. Because you need to show the graph does extend forever, right? Okay. I've done every kind of example for you except for one. Do you know what the one is? Let's see. Okay. Last one, f of x equals x squared minus 3x minus 4 over x minus 5. So let's factor. The numerator factors into x minus 4 times x plus 1. And then we have x minus 5 in the denominator. Okay, so first let's write the domain. All x's such that x can't equal 5. Good. Nothing to cancel, right? All right, time for intercepts. So x-intercepts come from where the numerator is 0. So just set x minus 4 times x plus 1 equal to 0. We get x is 4 and -1. But these are intercepts, so write them as ordered pairs. 4, 0, -1, 0. Then we need y-intercepts. Substitute in 0 for x. Go here. It's easier than substituting it into the factored version. So f of 0 would be -4 over -5, which is positive 4/5, but write it as 0, 4/5. You know what I mean? Jelly bean. Okay, good. Good. Okay. Asymptote time. So we have a vertical asymptote, right? Nothing canceled. So it's at x equals 5. Now, what's the degree of the numerator? It's degree 2, x squared. Degree of the denominator, 1. See how the numerator is exactly 1 degree higher than the denominator? That means we have an oblique asymptote. Or sometimes they're called slant asymptotes. It depends on your book. But it's slanted. So what happens is we're going to have the vertical asymptote, and then we have the oblique asymptote. It's going to be slanted like that. And you might say, well, what the heck does your graph look like, Professor V? It's either squished in the skinny part like that, or it could be out here lounging in the chunky part. So we'll have to figure out all that later. First, though, let's get the equation of this oblique or slanted asymptote, okay? It's going to be coming in at an angle, coming in hot. How do you get it? You long divide. So you look at the OG function right here, and you're going to long divide the denominator into the numerator. And you might go, oh no, I forgot how to do polynomial long division. Well, you are in luck. I really recently recorded another video on it. So I'll link it here. It's in the description too. I got you. So just look at the leading terms. What do you multiply x by to make it x squared? X, good. Then you multiply that through. I'm going to go quickly. If you don't remember how to do it, just go watch the video. It's not long. x squared cancels, and then negative 3x minus negative 5x is going to be 2x, and then bring down the negative 4. Then we repeat. So then you look, x into 2x plus 2, distribute 2x minus 10, subtract. These guys cancel. Negative 4 plus 10 is 6. This is the remainder. You ignore the remainder when you're finding the equation of the oblique asymptote, and you only look at the quotient right here. So it has y equals x plus 2 as the equation of the slant asymptote. So it's always y equals the quotient without the remainder. When you're in calculus, you'll see why, because the remainder will approach 0 as x gets large. Okay, so we've got 2 asymptotes to graph and then 3 intercepts. Let's see if it's enough info. And then don't freak out. When you graph this slant asymptote, all you do is graph it like you would graph the line, y equals x plus 2. Just think slope, y-intercept, and you just make it dashed, okay? Okay, so let's put the graph together. X, y. The vertical asymptote is at x equals 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, negative 5. 1, 2, 3, 4, 5. Oh, what happened there? 6, 7, 8, 9. 1, 2, 3, 4, 5. Okay, let me put the vertical asymptote in. X equals 5. And then here, the oblique one is at y equals x plus 2, right? Okay. How would you just normally graph that line? I would go, okay, the y-intercept is 2, the slope is 1. Rise 1, run 1. Yes? So y-intercept is 2. 2. Up 1 over 1. Honestly, it's easier. Figure out where it hits this guy. When x is 5, if x is 5, y is 7. So it should come through here. But this should just be a dashed line like this. Okay. Boop, 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 boop. Good? Yes, so nice. So I gotta see, is the graph sitting here and here, or is it out here and out here? So let me add more points. We have our x-intercepts 4, 0, negative 1, 0, and then 0, 4/5 is my y-intercept. Okay, so I know it's gonna be in this piece here, and then this piece here, right? Let me get this out of the way. It's stressing me out. Stop stressing me out. Okay, there we go. All right, so here's the funky thing. Like this part, I know. It's something like this. And you might say, but Professor V, like, where does it turn around? I feel really weird just graphing something. And I know. When you're in calculus, you'll do this. You'll figure out exactly where this point is. And in fact, I've graphed this exact problem in the Graphing Rational Functions video for calculus students. So if you want to watch it, it's linked in the description. And then same thing here. It's going to come up, 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 and then turn around somewhere. How do you know where? Well, because I've done this one using my calculus techniques, it turns around at 2.6 approximately, comma 2.1. But you wouldn't know that until you're in calc, okay? So you just turn around wherever your little heart desires. All right, but I know it looks like this because I've done this guy already. Okay, that's it. Yes. You feel all right? Do you feel slightly traumatized? I hope not. Let me show you. I graphed it in the calc problem and it looked more like that. Nice, right? So pre-calculus is exactly what it's called, a precursor to calculus. All of these topics that you're learning, you're going to build on, but you're going to look at them more from a conceptual point of view and understand what's going on behind the scenes, where a lot of the time in pre-calc, you're just kind of taught rules, right? without delving too deeply into concepts, but that's coming up. So hopefully you're excited to take calculus. It's so lovely. And that concludes the video. Oh yeah, please tell me, does anyone have to graph these with parabolic asymptotes? Because I'll do one for you, but I mean, that's rare. And if you need help with any other pre-calc topics, then check out the pre-calculus video lectures playlist. And if you're in calc and reviewing and you need help reviewing some algebra content, I have a whole playlist, Algebra Review for the Calculus Student. I also got videos for Calc 2, Calc 3, stats, lots of stuff. It's all organized into playlists, so check it out. And then follow me on Instagram and TikTok. We have lots of fun over there. Math with Professor V. I'll be back sooner than later, guys. I love you all so much. Bye.